So if we take a look, this first one is you need to use the mole fraction of the solvent. And then with the mole fraction of the solvent, you can then multiply that by the 135.3 torr, which is the standard pressure, and you should get 112.7 torr. Freezing point of a solution down here that contains 15 grams of ethyl glycol and 250 grams of water. So the first thing I'm going to do is I'm going to change that 250 grams of water to 0.25 kilograms. And I'm going to find the moles of ethylene glycol by getting molar mass. 2 times 12.01 plus 6.06 plus 2 times 16. Why are you so slow? So let's go to the calculator then. 2 times 12.01 plus 6.06 for the hydrogen plus 2 times 16 gives us 62.08. So we're going to take that 15.0 grams. Actually, I can just put it right here, 15.0 grams. I'm going to divide that by 62.08. 62.08 grams. 1 mole. 15 divided by, oh, she's not working at all today. Oh, there she goes. 15 divided by 0.25 divided by 62.08.
That would be about 0.9664.
So 0.9665 molal. We're then going to multiply that by, what's the index for this one?
1.86.
Nope, the index isn't 1.86.
Oh, sorry. The index is 1.
The index is 1. What is it? Degrees Celsius per molal. The index is 1 because this is a molecular compound, C2H6O6. It doesn't break down or dissociate into more than one thing. 0.9665 times 1.86.
It's about 1.7976.
That rounds to 1.8 degrees Celsius. Why then is the answer negative 1.8?
Because it's a depression from the original, which is 0.
The original freezing point for water is 0 degrees Celsius. And it's freezing point depression, so we need to subtract that 1.8 from 0. Cool. During Wisconsin winter, the temperature can reach negative 25 degrees Celsius or colder. How many grams of antifreeze, ethylene glycol, would you need to add to your radiator to keep 7.5 liters of water from freezing? Assume that it's 1 to 1. So that means that 7.5 liters is 7.5 kilograms. We are looking for this X right here, which is the number of moles, which we're going to want to change to grams. Ethylene glycol, we just said that it does not, the index is 1 because it does not dissociate. Man, you guys, the odds are basically all the same problems, huh? This problem is basically the same as that one up there, except for we're solving for something not the final temperature. We want it to be equal to 25 degrees Celsius. So we need to solve for X. To solve for X, we'll multiply both sides by 7.5 and divide by 1.86. That'll give me that number of moles. 25 times 7.5 divided by 1.86. That gives me 100 moles, 100.81 moles. Looks like we're gonna have 2 significant digits at the end of this. And then we need to change every 1 mole as a mass of 62.08 from the other problem. We already found that up here. That's how many grams it is. So 100.81 times 62.08. We're going to round that to 2 significant digits. which is going to give us 6,300 grams. Questions there? I would definitely suggest you try some of these other problems. I'll try to get the answers to these up there by the end of the weekend. Anybody want to see any from 7 through 12? Right now? No, no, no. All right. Cool. Then we will talk about stoichiometry. And then the group that's coming tomorrow is going to make a solution. We want to talk about that. We want to make sure that they can get part of a procedure today to make it. And we're going to use that solution next week for our Spec 20 lab. All right. So let's do the stoichiometry. I'll do a few problems here, and then we'll talk about making that solution for that group. So basically, when we add molarity to stoichiometry, it only does one thing. For example, we have to realize or recognize that 0.200 molar is 2.200 moles per liter. And basically go from there. So it says calculate the mass of silver sulfide. So we want in the end grams of silver sulfide. How many units is that?
1.
1 unit. So I'm going to start with 1 unit. Which of these, 125 or the other one, which one of those has 1 unit?
The 125.
125 milliliters. Right? $125 milliliters. Every 1,000 milliliters is 1 liter. For this solution, the silver nitrate, if we have 125 milliliters of the silver nitrate, every 1 liter of that has 0.200 moles. When we look at this, every 2 moles of the AgNO3, here's our stoichiometry step. Every 2 moles of the AgNO3 will make 1 mole of Ag2S. And we don't want moles of Ag2S, so we need to change that. Every 1 mole of Ag2S is how many grams? 107.87 times 2 plus 32.06.
The answer is 247.8.
247.8. 125 divided by 1,000 times 0.2 divided by 2 times 247.8.
That would be 3.0975.
3.10 grams of silver sulfide. There we go. Questions there? No. So if you do the next one, what are you going to start with? 100 milliliters or 0.42 moles per liter?
100 milliliters.
Yeah, right? 100 milliliters. 100 milliliters. Here, what mass of iron is produced when 35 milliliters of this is mixed with 55 milliliters of this? Well, what type of problem is that bringing back?
Like the limited reagent problems.
Yeah, that's a limiting reagent problem from last semester. You got to do both problems, and then whichever one creates the least, that'll be the amount. Five. What was the molarity of this solution? Well, let's do this one because this is going to find molarity. This is a little bit different. So we got to write a balanced equation for it. We have sodium sulfate reacting with barium chloride. What type of reaction is this going to be?
Double replacement.
It's going to be a double displacement reaction. So if we're looking at a double displacement reaction there, what are our products going to be?
BaSO4 and NaCl.
BaSO4 plus NaCl. Is it balanced?
I think we need to add a 2 to the NaCl.
We need to add a 2. Since we have 2 NAs here and 2 CLs here, we need to add a 2 there. I'm not sure if that's going to even affect us on this, but that's needed to do balance it. So we are reacting 5.28 grams. I'm sorry, 5.28 grams of this is made, right? We want to figure out what the molarity of this is. So if we can figure out how many grams of this was made, we can figure out how many moles of this we have. So let's do that. BaSO4. Every 1 mole of BaSO4 is so many grams of BaSO4. And every 1 mole of BaSO4 requires 1 mole of sodium sulfate to be made, or to be used. That'll get us the moles of sodium sulfate. If we have the moles of sodium sulfate and we divide by the volume, which is 0.250 liters, we will have the molarity. So let's figure out the molar mass of barium sulfate. 137.33 plus 32.06 plus 4 times 16.
The answer is 233.39.
233.39. 5.28 divided by 233.39.
The answer is about 0.02262.
2262. 0.02262307772 divided by 0.250.
It's 904,900,000.
She didn't hear my point. 0.02262 divided by 0.250.
It's 0.09048.
0.090. The 250 here. The 250 here actually only has 2 significant digits. So we can get rid of that. And that is our moles per liter of sodium sulfate. Questions about what I did there? Keep in mind, I had the grams of this, so I could find the moles of any one of these up here. Since I knew the volume of that solution, all I needed to do to find the molarity was to put it into divide the moles by the volume of the solution in liters. Now, another way I could have done this problem, which I wouldn't probably do myself, but since I needed 2 units, I could have easily started with 5.28 over that liters, but that just seems weird to my mind. But if it's fine, if you're like, whatever, I can see math or whatever, then by all means, you can go for it. So you guys should practice with 2, 3, and 6. problems 2, 3, and 6. If you take a look under assignments and solutions on Canvas, there is a laboratory called the Spec 20 laboratory. I'm going to pull that out real quick just to use to write on and stuff. So if you want to print a copy of that out real quick as well, you can. There's no other way to get to it besides going through assignments. I don't think it's on anything in the under the current work button yet, because the main laboratory we're going to do next week. But in order to do it next week, we need to make, first off, the solution that we're going to use. One of the Indiana State standards is that you make a solution. I'm gonna go grab that off the printer real quick and I'll be right back. Let's fly through an idea real quick. Let's imagine that you have a sample. Of just solvent. What's a good solvent? Universal solvent?
Water.
Water, right? And we shine light through this. We have something over here that reads that amount of light. This would be what we call transmittance. If we take the reverse of that, we can find what's known as the absorbance. Let's imagine then we take another sample and we shine light through it. But this is solvent. Let's say it's saturated and solute. Is as much light going to shine through?
No.
Right. As the light hits through there, it's going to bounce off of these particles that are floating around in there, right? I'm going to make a smaller arrow. And less light. If less light is through, that's less transmittance or more absorbance. Let's say we did this a few times with many different dilutions. We performed this several times with many different dilutions. We will actually be able to graph. Let's see. Independent variable goes on the bottom. So that would be concentration. Right? Independent variable on the bottom, like time, right? And absorbance. Absorbance would go on this axis. You would be able to plot your different points. We said that as concentration goes up, more absorbance occurs. So when concentration is low, lower absorbance is there. What other line does it have to go through? Well, didn't we say if there is zero concentration, then how much absorbance is there? Only going through solvent.
There's no absorption.
Yeah, right? So we have to go through the 0 point, right? Boom. Now, what if I gave you a solution and I did not know the concentration of it? Well, you could put it into this machine, drop it in there, measure the absorbance, find the absorbance plot, the point, and go down here and get the concentration. And you could do that very fast. Hey, I need this 100 samples figured out. Okay, I've got the absorbance line of that. There's sample 1, sample 2, sample 3. Would be pretty quickly done. Well, what if you were looking at concentrations of, let's say, a pesticide in a local water table? You could sit there and go to many different water samples around the county, collect them, and then put them through this machine and test for those. And this, what this device is called, it's called a spectrophotometer, and this we use what's called the Spec 20. You probably have seen this on crime shows and stuff like that many times if you're into crime shows or something like that. Basically, it's got a 1980s. Can I draw this even? I don't even know. But it's got like a 1980s number system on it. And it's got 2 knobs on there that are analog. And then on here, it reads off a number in that, in those old calculator forms. Here is where your sample goes. And in here, there is a light bulb that basically shines light through that sample. And over here is a photometer or photometer, which measures the photons, the light photons. This machine changed the way a lot of scientists were able to conduct experiments. It's pretty cool. And I think it's going to be cool for those of you that get to use it. All right, so that's easy enough. Hopefully that little mind game or whatever made some sense. If not 100% sure on that, no biggie, because that's next week. Let's take a look at page, oh, there's no pages. Page 1 of the report sheet. So it says, a stock solution of copper 2 nitrate hexahydrate was prepared by dissolving 1.462 grams of solute in 25 milliliters of solution. You will need to calculate the original molarity of the stock solution. So what do we need for molarity?
Moles of solution over, or moles of the solute over liters of solution.
Very good. Moles over liters. So here we have moles over liters. Here's milliliters. So we can put that on the bottom. That's 0.025 liters. Here's grams. We can get the moles from grams. One thing is we don't deal with hydrates very much. You remember how to get the molar mass of a hydrate? You have to add up 6 waters and add it to whatever the molar mass of this is. So 6 times 18.02.
The answer is 108.12.
58.93 plus 2 times 14.01 plus 6 times 16.
It's 182.95.
182.95 plus 108.12.
The answer is 291.07.
1.462 divided by 0.025 divided by 291.07.
It's about 0.2009.
So 0.2009 moles per liter. Now notice, you have to think almost that this person was probably not trying to make a 0.2009 moles per liter solution. They were probably trying to make a 0.200 molar solution. But when they got to their scale, they ended up with a little bit of extra mass of the stuff. That's going to happen. Even for those of you that are coming in to do it, what I would like for you to do tomorrow is make 100 milliliters of 0.200 molar cobalt 2 nitrate hexahydrate. You'll be using one of these. This is a volumetric flask. So if you take a look right here, there's this line right there. If you fill this all the way up to that line, that will be 100 milliliters. And if we remember, every time when we look at the these solutions, we never say, take this salt and put it in 100 milliliters of water. We always say, fill it up to 100 milliliters. And that's why we do that. We fill it up to 100 milliliters. So in order to make this solution, we need to get a procedure. The only major thing that we need to know for this procedure, other than actually physically doing it, is the mass of the cobalt 2 nitrate hexahydrate we need to put in there. Because you can put that mass in here and you can fill that up to the 100 milliliter mark on the water, then you're good, right? That is the procedure for making a solution. So what I'd like to do is, who do I have that usually comes in? Emma, Claudia, Noah, Jonah, and is he not here today? What's the other kid? I can't think of it. We usually have 5, right? So it only looks like 4 of you are in here. Is Claudia in here? Oh no. So I'm going to put you guys into 4 rooms and you'll discuss basically how to make these solutions. I'm going to put Emma in 1, Noah in 1, and Jonah in 1 because those people actually come. And then we'll make another group of people who don't come, and you can discuss it as well. That way, tomorrow, whenever you, if you end up joining up with Claudia, you can try to bring her up to speed on it. Hopefully, if she gets a chance, hopefully everything's okay, and she gets a chance that she can watch this video because I am recording it. So,
Mr. Jackson.
hey, what's up? Oh, Owen
coming.
comes too, doesn't he? All right, then I'll put you with Owen. Thank you, Owen. I got you to talk. It was all part of my plan. So let me just make sure here. Move to room 3. Move to room 4. And move to room 2. All right, I think this works. All right, if you do have questions, please invite me to it. I will type into all the groups what you need to do. And basically that is just make 100 milliliters of a 0.200 molar cobalt nitrate hexahydrate solution. All right.
Are you like using two different screens or something?
Yes. Whoa, this is a long lab. Okay. Sorry, I'm trying to get it pulled up. This is taking a long time.
Oh, I gotta print this off. This is gonna be a whole lot of work for you to do on your own. Like in the lab.
So. Um,
I'm trying to remember. Did he say how to make it or figure out the?
Yeah, how to make
Oh,
100 liters of a 0.200 molar cobalt-2 nitrate solution.
okay.
Yeah.
Uh,
Wait, who's going in person tomorrow?
I am.
Okay.
I think I'm the only one that's not going in person.
No, I'm not either.
Oh, okay.
We got a procedure yet?
I have one.
Are you sharing the screen with everybody so they can see, or no? Do you not have the ability to do that?
Well, I mean, it's written down, so I don't know if sharing the screen is really gonna help.
Okay. Walk us through it. Let's see what you got.
Well, when I calculated it, so if you want 0.200 molar of 100 milliliter solution, I first calculated how many moles needed, which is 0.02 moles. And then I calculated the molar mass of the cobalt nitrate hexahydrate, and that's 291.07 grams per mole.
Mm-hmm.
Then I multiply that by the 0.02 and
Mm-hmm.
got 5.8214 grams. And then you add that to the beaker, and then you add enough water to get to 100 milliliters to get the solution.
Good, good. What size beaker?
Well,
This is where it gets kind of tricky, where the math doesn't show us the techniques, but that sounds good. What I would suggest is maybe a 50 milliliter beaker.
Okay.
and then add water to dissolve it. And then pour it into the volumetric flask. And
And
then,
then add more water.
and then rinse out that beaker. Keep rinsing out that beaker over and over again with water and pouring it into that until you get up to there. So it makes
Okay. Yeah.
cool. So you want to make sure that Noah, that you get a copy of that somehow, that procedure.
I can type it in the chat. if you
Okay,
want.
cool. Or maybe just send a file or something through email or through Canvas. Cool, cool.
Yeah.
So do we have a procedure for this group?
Wait, did we have to make a whole procedure or just a procedure to get the mass?
Basically, Owen needs to kind of know what he needs to do with that mass when he comes in tomorrow.
Okay, then we don't have a procedure. All we did was figure out what the mass needs to
What
be.
did you get?
I got 36.6 grams.
That seems very high. Did you count the hydrate, the 6H2O?
Oh no, I did not.
So you need to correct that. 2.
Yeah.
Okay. So what's next?
Wait, we have fine massive cobalt. And then
Okay, if we're trying to do, okay, hold on. 100 milliliters is 1 liter of water. So we need to have 0.2 moles of the
wait, isn't
substance.
there already a procedure written? Wait, now I'm really confusing myself.
Is there?
Look on page 2.
Wait, what? Oh.
The whole procedure is typed out.
Stop. What? Wait, hold on. This is. Wait, this is not the same thing. This is definitely not the same thing. Right?
The procedure for something is all typed out.
I don't think this is the right one.
So this laboratory is the one for next week. There is no procedure for making the chemical to start the lab.
Okay.
Right? So basically all you need to do is figure out how much salt to put into the water. And then you just need to physically be able to do that tomorrow. That's
Where
your,
do we write all this down at?
where's what?
Where are we writing all this down at?
On a piece of paper. Anywhere you want.
So there's nowhere on the lab to write it?
Nope, there is not.
Oh.
Nope.